Today we're going to go through an example of writing down a matrix that transforms the Cartesian plane. So we're going to find the matrix A that transforms the Cartesian plane by doing a few things. First, it stretches the plane vertically by a factor of 2. Then this matrix stretches the plane horizontally by a factor of 1/2, or in other words, we could say it also shrinks it by a factor of 1/2. And then it rotates the plane counterclockwise about the origin by an angle of pi/4. So we're going to answer this question by actually constructing 3 matrices, but I'll talk about that in a minute. The main idea that I want to point out is that we're interested in 2 very special vectors. The first one we call E1, and this is the unit vector that points in the x direction. So it's the vector 1, 0. Next, we're interested in the vector E2, which is the unit vector that points in the y direction, and so this is the vector 0, 1. Now we talked about how these vectors, 1, 0, and 0, 1, can be used to construct any of the vectors in the Cartesian plane. So if I find out what happens to each of these vectors, I can then find out what the matrix is that will transform all vectors in the Cartesian plane. So the way we build those matrices is we write down in the first column, we write down what happens to E1. So this column is where E1 ends up. Oops, let me scroll up a little bit here. So we would have 2 elements here because this is going to be a 2 by 2 matrix. And the second column, where again we'll have 2 elements, this is going to be where E2 ends up. All right, so let's get started with this problem. Okay, I'll just scroll down a little bit. I have the problem just restated here. And my plan is to write down 3 matrices and then multiply them in a way that constructs the matrix A that I'm looking for. So the first matrix I'm going to write down, I'm going to call it A1. This will be the matrix that does the first thing we want it to do, which is stretch the Cartesian plane vertically by a factor of 2. That'll be A1. Then we'll find the matrix A2, which does the second operation we'd like, which is, or the second transformation that we'd like, which is stretching the Cartesian plane horizontally, by a factor of 2, of 1/2. Okay, and lastly, A3 will be the vector that rotates the Cartesian plane counterclockwise by an angle of pi/4. Okay, so I'm going to find these 3 matrices that do the 3 different transformations that I am looking for. And A, the matrix that we ultimately want to find, is going to be the product of these matrices. We have to be careful about the order in which we take this product. So A, this matrix A, if I can scroll up a tiny bit, is going to be the product of these 3 matrices where the transformation that you want to happen first should be on the right. So A1 is the transformation we want to happen first. That'll be on the right. And we move from right to left. So the next transformation we want to happen is A2, and the last transformation we want to happen is A3. So we'll take this product of matrices at the end. The reason that we write it in this order is that when we multiply a matrix times a vector, say we had some vector V over here, the first matrix that would multiply it is A1. That would be the first matrix that kind of hits V, and the first matrix that transforms V. The next transformation would be the next matrix that is multiplied, and the last transformation would be the last matrix that gets multiplied. So that's why the order seems a little bit backwards, but this is actually the correct order we want. All right, so let's go ahead and start with finding A1. The matrix that stretches the plane vertically by a factor of 2. So we want to think about what happens to E1. This is, remember, the vector 1, 0. Where does that end up? And we also want to look at what happens to E2. Remember, this is the vector 0, 1. We want to ask where does that end up? All right, so if we're stretching vertically by a factor of 2, let's consider E1. E1 does not have a vertical component. Its vertical component is 0. So if I were to stretch this vector vertically, nothing would happen because I can't make, it doesn't get thicker or anything like that. It can't go anywhere. So E1 actually just remains at 1, 0. E2, on the other hand, if I stretch the plane vertically by a factor of 2, E2 has a non-zero vertical component, and so it will get stretched by a factor of 2. So maybe I'll draw that. E2 will get stretched, and E2 will end up at the vector 0, 2, because that is 2 times E1. So A1, the matrix, my first transformation matrix, is going to be a 2 by 2 matrix where the first column is where E1 ends up. We just saw that that ends up at 1, 0. It doesn't go anywhere. And the second column is where E2 ends up. And we just found out that E2 ends up at 0, 2. So this is our vertical stretch by a factor of 2. Let's go ahead and find E2, the horizontal stretch, by a factor of a half. And again, we want to find out where E1, the vector 1, 0, ends up, and where E2, the vector 0, 1, ends up after we stretch it by a factor of a half. Now in this time, E1, if we stretch E1 horizontally, it has a non-zero horizontal component, so it'll be stretched horizontally. But a factor of a half is actually going to be kind of shrinking the vector down a little bit. So if I did 1/2 times E1, I'd end up here. So E1 is going to end up at the vector 1/2, 0. Similarly to the case for E1 in the last example, E2 this time has a 0 horizontal component. So I can't stretch or shrink 0. So nothing's going to happen to E2. It'll just stay where it is. So E2 goes to itself. And now my matrix that does the horizontal stretching is going to be given by 1/2, 0 in the first column. Remember, that's where E1 ended up. And 0, 1 in the second column, because that is where E2 ended up. It just happened to not go anywhere. All right, so there's A2. Let's go ahead and figure out what A3 should be. So there are 2 ways you can approach this problem. You can do what we did in the last 2 examples and try and kind of figure out where E1 and E2 end up. Or we can use the rotation matrix that we derived in class. So the rotation matrix, that's given by cosine theta, sine theta in the first column, minus sine theta, cosine theta in the second column. All right, and this is a counterclockwise rotation by an angle theta. So if we want to rotate counterclockwise, CCW is my abbreviation for counterclockwise, by pi over 4, then I would just plug in pi over 4 for each value of theta. So my matrix A3 is going to be cosine pi over 4, negative sine pi over 4, sine pi over 4, and cosine pi over 4. And if I evaluate all of those, I get square root of 2 over 2, negative square root of 2 over 2, square root of 2 over 2, and the square root of 2 over 2. And that's my matrix A3. So our last step is to put all of this together. All right. So remember, at the beginning of this example, we wanted to find a matrix A that does all 3 of these operations in this order. So to find A, I'm going to multiply in that order that we talked about earlier. So A1 will be on the right, A2 will be next, and then A3 will be on the left. And I want to do this whole matrix multiplication. So I'm going to have root 2 over 2 and root 2 over 2 in the first column, negative root 2 over 2, root 2 over 2 in the second column. That's A3. A2 is a half, 0, 0, 1, and A1 is 1, 0, 0, 2. Okay, now we're just going to multiply all these matrices together, and you could, you could multiply these two first, and then multiply this one. You could multiply these first, and then this one. I'm going to multiply A1 and A2 first, and then I'll multiply A3 next to it. So I'm going to leave A3 alone for now. 2 over 2, root 2 over 2. Okay. And if I multiply A1 and A2, I'm going to have 1/2 times 1 plus 0 times 0. So in this first column, in this first row, first column, I'll have a half. And then I'll have 1/2 times 0 plus 0 times 2. So in this first row, second column, I have 0. And then I'll get 0 times root 2 over 2, and then, oh, sorry, I'm getting ahead of myself. 0 times 1, 1 times 0, I'll get 0. And 0 times 0, 1 times 2, I'll get 2. I almost started multiplying A3 there, but that's the next step. So if I then multiply this matrix by A3, my final answer is going to be that A is equal to, let me scroll down a bit so you can see. Sorry, I need to give myself a little more room. There we go. A is going to be equal to root 2 over 4, negative root 2, root 2 over 4, square root of 2. And now this is my final answer. This is the matrix that does all three of those transformations in the required order.